Have you ever really stopped to think about what's going on inside your computer? I mean, you click a button and poof, magic happens. Well, it's not actually magic. It's a beautifully organized process. And in the next few minutes, we're going to pull back that curtain and show you exactly how the machine on your desk really works. So let's start with something super simple. You type 5 plus 5 and hit enter, and instantly the answer 10 pops up on your screen. But what actually happened in that split second? Between your finger hitting the key and that 10 appearing, there's an entire universe of operations happening at lightning speed. We're going to trace that exact journey, step by step. And this is our map for that journey. Now, I know it might look a little technical at first glance, but believe it or not, this diagram shows the fundamental path that information takes inside every single computer. It doesn't matter if you're editing a video or just browsing the web. It all follows this exact flow. This basic design is what makes all modern computing possible. At its core, this whole map follows a simple 4-step dance. It's often called the input-process-output cycle. First, you give it input. In our case, that's the 5, the plus, and the other 5. Then, the computer's brain will process that data, do the actual math. Next, it gives you a meaningful result, the output. That's the number 10 on your screen. And finally, if you wanted to, you could use storage to save that result for later. Input, process, output, and sometimes storage. That simple loop is the blueprint for everything a computer does. Okay, so let's start our journey right at the heart of the machine, the processor. You've probably heard of it as the CPU, or the central processing unit. This is the engine. This is where all the thinking actually happens. Deep inside that CPU, we find a component called the arithmetic logic unit, or ALU for short. The easiest way to think of the ALU is as the brain's own personal calculator. Its job is actually pretty straightforward. It handles all the math, addition, subtraction, you name it, and all the logic, like comparing if one number is greater than, less than, or equal to another. It's the part that does the real number crunching. Now, if the ALU is the calculator, then the control unit, or CU, is the traffic cop. See, the control unit doesn't do any calculations itself. Instead, its critical job is to manage the flow of everything. It fetches instructions from memory, and then it tells the ALU what to do and when to do it. It's the manager that makes sure everything happens in the exact right order at the exact right time. So when the CPU needs to add 5 plus 5, where does it hold those two 5s? Well, it uses this tiny, ridiculously fast bit of memory called registers. Think of it like a little scratch pad built right onto the CPU chip itself. This is where it keeps the data it is literally working on at that very nanosecond. It has to be right there to keep things moving at full speed. And just how fast is full speed? Well, modern CPUs are measured in gigahertz, or GHz. 1 gigahertz means 1 billion cycles per second. So that whole process of fetching an instruction and calculating it can happen over 1 billion times in the time it takes you to snap your fingers. The speed is just staggering. So the CPU is incredibly fast, but it can't hold very much data on its own. It needs a place to pull instructions from and a place to put the results. And that brings us to memory. But here's the thing. Not all memory is created equal. It's all a constant balancing act between speed, size, and, of course, cost. This pyramid shows that balancing act perfectly. Right at the very top, you have those super fast but tiny CPU registers we just talked about. But as you move down the pyramid, the memory gets a lot bigger and a whole lot cheaper. But it also gets much, much slower. Understanding this trade-off is probably one of the most important concepts for knowing how computers really work. The two main levels you'll probably hear about are primary and secondary memory. A great way to think about it is this. RAM, or primary memory, is like your desk workspace. It's fast and it holds everything you're working on right now. But when you turn the power off, your desk gets wiped clean. That's what we mean when we say it's volatile. Your hard drive, or SSD, on the other hand, is the library. It's slower to get things from, but it stores everything permanently, even when the power is off. It's non-volatile. There's also one other special type of memory called ROM, which stands for read-only memory. This is a permanent, non-volatile chip that holds the computer's most basic, fundamental startup instructions, something called the BIOS. When you press that power button, the BIOS is the very first thing that runs. It's like the computer's wake-up call, telling it how to check its hardware and find the operating system to get everything started. All right, so we know how a computer thinks and how it remembers, but how do we give it the data to think about in the first place? Well, that brings us to the whole world of input devices. And it's not just about your keyboard and mouse. There are some really cool specialized input devices out there. For instance, an OMR, an optical mark reader, is what scans the bubbles on an exam sheet, or the barcode reader at the grocery store. There's even a wild one called MICR, which uses special magnetic ink to read those funny-looking numbers at the bottom of a bank check. So that's how we talk to the machine. Now for the other half of the conversation. Once the CPU has done its job, how does the computer talk back to us? The answer, of course, is through output devices. Now, besides our screens, printers are a classic output device. And they basically fall into two camps. You've got impact printers, like those old noisy dot matrix machines. They physically strike a ribbon to make a mark, which is why they're great for things like train tickets that need carbon copies. Then you have non-impact printers. Those are the quiet ones we all use today, like a laser printer using toner or the thermal printer at the ATM that uses heat to print your receipt. So whether it's a keyboard or a printer, all these devices are just channels for data. And this brings up a really crucial point. Computers are incredibly fast and they are perfectly logical, but they aren't smart. They just follow instructions perfectly, which leads to this famous old saying in programming, garbage in, garbage out, or GIGO. It means if you give the computer bad information, it will flawlessly process that bad information and give you a perfectly bad result. Speaking of all that data, whether it's garbage or not, how do we actually measure it? To really get a feel for the scale of information our computers handle, you have to understand its language. And in the digital world, the magic number isn't a nice round 10 or 1,000. It's 1024. See, it all starts with one bit, a single 0 or 1. You put 8 of those bits together, you get 1 byte, which is about enough to represent a single letter, like the letter A. Now here's the trick. Because computers think in powers of 2, everything scales up by 1024, which is 2 to the power of 10. So 1024 bytes is a kilobyte. 1024 kilobytes is a megabyte, and so on all the way up. That's the language of your file sizes and your hard drive capacity. And there you have it, the whole journey from your fingers to the screen. Data flows from an input device, gets crunched by the CPU using its memory, and then gets sent back to you through an output device. That simple loop, input, process, output, is the very heartbeat of your computer. And when you repeat that loop billions of times every second, well, that's how we build our entire digital world. The only question left is, what are we going to build with it next?